All right, so welcome to the latest installment in this series of screencast videos for Math 1410, Elementary Linear Algebra. For those of you who skipped the Chapter 1 videos, welcome to your first of these videos. And in case you did miss the videos for the first chapter, let me just remind you that there are a few things that you should probably be doing as you watch these videos. Keep in mind that you can control the videos. So unlike with a lecture, if you want to pause, rewind, you can do so. You can also change the speed at which things play back. On most web browsers, if you right-click, you can access some media controls to allow you to change the playback speed. So you can go fast through the parts that you're comfortable with, or the boring parts, whatever, however you want to call it. And you can slow things down when you get to something where you need to kind of go through it a little bit more carefully, or you can rewatch. And it's a good idea to stop anytime you encounter a new concept, make a note of it, keep track so that you're familiar with it, and make a note of anything where you didn't quite understand it the first time you saw it, because often you've got to go back and you've got to look at things 2, 3, 4 times before it really starts to sink in. And one of the ways you can do that is to see it in various different ways. So see it on these videos, then go take a look at it in the textbook, then come and ask about it in lecture, ask about it in tutorial, ask about it in office hours, and keep chipping away at things until they settle in. And it's not a bad idea as you go to do some of the exercises in the relevant section. Maybe try to make your own examples. Have pen and paper with you as you work through these videos. Okay, so this video is going to introduce the basics of the complex numbers system. So the set of complex numbers is denoted by a capital C, and it's defined as a set of binomials. So the definition looks like this. It's all numbers of the form x plus I times y. X and y here are just ordinary real numbers. The new character here is this number I. So I satisfies the property that when you square it, you get -1. Now we know that I cannot possibly be a real number. In the real numbers system, whenever you square a real number, it always comes out to be bigger than or equal to 0. It's impossible to square a real number and get something like -1, which is negative. So this is an entirely new number, if you like. One way to think about it is to say, well, okay, this I is, it's the square root of -1, the positive square root of -1, if you like. Now, complex numbers have been around for a long time, and they've been making people uncomfortable for just as long. It really doesn't seem to make sense based on your everyday experience to be able to square a number and get something which is negative. But you can find them going all the way back to 16th century Italy. There were a number of texts produced at that time developing algebraic methods for solving equations, and you will find people using complex numbers back then, but they weren't really open about it. This was not something that was viewed as uncontroversial. It seemed like a really strange thing, and so people like Bombelli were using complex numbers to solve equations, and they were coming up with answers, but in the text that they were writing, they were simply providing the answers without saying how they came up with them, because they didn't actually want to admit that they were using complex numbers, because this was something that they thought their colleagues would frown upon. And because these weren't really accepted, you didn't really see much use of them for quite a long time until people like Euler and Gauss come along, and they start investigating the properties and realizing that there is actually quite a bit that you can do with complex numbers. And one of the big steps in getting complex numbers accepted was development of a geometric interpretation for the complex numbers. So we'll see that one of the ways you can think about the complex numbers is as sort of a two-dimensional number system. You have two variables, x and y, and so you can think of the complex numbers as being something which is geometrically similar to the Cartesian plane. You have two coordinates, so you can think of it as a two-dimensional coordinate system. And from that point of view, a lot of the arithmetic with complex numbers actually starts to make sense. The development really took off in the 19th century. The biggest name in complex analysis is Cauchy, Louis-Augustin Cauchy, who pretty much developed this subject to the point that you find in a lot of undergraduate complex variables textbooks these days. Others like Riemann took over and kept developing the subject, and there was a lot of interesting stuff that came out as they worked through. And by the end of the 19th century, complex analysis in its sort of modern form was already in existence. Now, I mentioned that Bombelli was using complex numbers to solve equations. Now, what sort of equations was he trying to solve? He wasn't trying to solve quadratic equations, right? So a lot of people say, well, why do you introduce complex numbers? You introduce complex numbers because you want to solve something like x squared plus 1 equals 0, right? So if you were trying to solve this, you would say, I don't know, maybe you would just simply move the 1 over and say, okay, x squared is equal to minus 1, and then you try to take the square root of both sides, and you say, I've got to take the square root of a negative number. How do I do that? But for mathematicians in the 16th century, this was a non-issue. These were people that were being brought up in the tradition of Descartes and analytic geometry, and so for them, the solution of an equation like x squared plus 1 equals 0, or really the solution for any sort of equation, any polynomial equation, was they were simply figuring out where the graph of that function crossed the x-axis, right? So if you take something like x squared plus 1 equals 0, if I take y equals x squared plus 1 and I plot it in the Cartesian coordinate system, well, you get a parabola that is opening upwards with its vertex here at 0, 1. And so there are no x-intercepts. It doesn't cross the x-axis, so the fact that there were no solutions to an equation like x squared plus 1 equals 0 made perfect sense. There shouldn't be, because the graph doesn't cross the axis. But the trouble is you then get to cubic equations, and for any cubic equation, if I have y equals x cubed plus maybe some other stuff, and I plot a graph or something like that, well, it's always going to look something like this. It might have a little bit of a bump somewhere in between, but it always goes down to minus infinity in one direction and up to plus infinity in the other direction, and so there definitely is a point of intersection. There's a point where it always crosses the x-axis. So they know there has to be a solution, but depending on the values of p and q, sometimes in this form here for a cubic, there are going to be some scenarios where you can't solve it using the known formula. So the formula that was known at the time was due to Cardano. It's here on the screen. It's a very complicated looking formula. This is not something I expect you to actually write down. Don't write it down. You don't need to know this formula. It will never come up again in the course. But notice the q squared minus p cubed under the square root. It's not very hard to come up with examples where q squared minus p cubed is a negative number. And if it's a negative number, then, well, how are you going to get an answer? How do you solve for x? It seems like the formula is wrong. There's something wrong with it, and it's not going to work out. But what Bombelli realized is that if you allow for complex numbers, if you allow for a negative square root and you just treat this as a complex number, well, then you're dealing with the cube root of a complex number, and you have to understand how that works. We will go over things like that. But you can play around and you can realize that these two terms, the first term, this guy kind of ends up being of the form like a plus b times I. So you get a complex number. The square root of minus 1 shows up. And the other one, what Bombelli realized, is that if you allow for complex numbers, in this formula, in this cubic formula, they always showed up in pairs like this, where the first term, whatever number was in front of I in the first term, the negative of that number showed up in the second term. And so when you added the two of them together, the i's canceled out and you just got 2 times a, you got something which was real. And that meant that he was able to still use his formula and get a solution, a real number solution, and tell people what that solution was. The only thing he couldn't do, or wasn't willing to do, was tell people how he came up with that solution. Okay. So, there's, I guess, this is sort of still, I guess, a fairly esoteric reason for wanting to work with complex numbers. It's not something which seems particularly applied, although it was certainly of interest to people back in the 16th century. Nowadays, complex numbers, they do show up. They're all over the place. You can't do physics without complex numbers. They show up in quantum mechanics. They show up in electrical engineering. They show up in image processing. They're essential to a lot of modern day applications that require mathematical application. You really can't get by without them, despite the strangeness that people tend to feel when they first deal with complex numbers. Now, I mentioned that one of the ways you can kind of feel a little bit better about complex numbers is to have a good geometric interpretation. And so the interpretation that Gauss and independently Argon came up with was to view the complex numbers as a coordinate plane. Now I'm drawing the complex numbers as vectors. In chapter 3 we'll start talking about vectors. And so the idea is that you label the horizontal axis as x as usual. The vertical axis you think of as I times y. So this is sometimes called, we'll see in the next couple of videos, that the term with the I in front of it, the term with the square root of -1, for historical, unfortunate historical reasons, is sometimes called the imaginary part. And so the vertical axis is sometimes called the imaginary axis. And so a complex number, it can just be viewed as a point in the plane, or as a vector, depending on your point of view. So this might be, maybe this is 1, 2, 3, 4, 5 units out, and 1, 2, 3 units up. So this might be, say, the complex number 5 plus 3i. This number down below looks like it's well, it's the same distance out, but it's maybe not quite as far down. So maybe this is, say, 5 minus 2i, and so on. So you can these two real numbers that make up the two parts of a complex number, these numbers x and y, you can just think of them as coordinates in the plane. And so you do have sort of a nice concrete geometric reality to these complex numbers. But what's going to make them interesting, what we'll see in the next video, is that you can also do arithmetic with complex numbers. You can add them, you can subtract them, you can multiply them, you can divide them. In fact, any kind of arithmetic that you can do with real numbers can also be done with complex numbers, and that's where things will start to get interesting. Okay, so we're going to stop here.